All right, today we're going to talk about a topic called linear programming. It's not the kind of programming you might think it is with computers. Instead, although I'm sure you could do some programming to solve these problems, instead, what we're going to do is related to the last topic we talked about, which was systems of inequalities. Okay, and we did all that shading and graphing, dash lines and solid lines and all that stuff. And so it's an application of that. And so there are going to be two things that you really need to keep in mind as we go through a linear programming problem. Basically, the system of inequalities, the shaded region that we talked about last time, is going to be what we call the constraints. Okay, the constraints are basically a set of inequalities, that place limitations on a situation, whatever the situation is. Okay, they put limitations though. That's the main thing. So the constraints are a set of inequalities that put some sort of limitations on things. The other thing we're going to have to keep in mind is something called the objective function. The objective function is it's the quantity that we're trying to either maximize or minimize. So it is a quantity that we are trying to, I'll call it optimize, but really that means minimize, or maximize. So it's a quantity that we're trying to optimize under the given constraints. Okay? So let me give you just a quick example of something where that might happen. I'm not going to give you, all the details of equations, but just a scenario where this could happen. Something that we're dealing with right now is, of course, the coronavirus and all the, social distancing and isolation and all this stuff that's going on. And so one type of objective function, one thing that we might be trying to optimize, in this case minimize, is the number of deaths caused by the coronavirus. Okay, the number of people who die. That would be something we might want to minimize. Okay. Now, the number of people who die from coronavirus is directly related to two things, in my opinion. This is just my opinion. The first thing is the number of people who get infected. Okay, as that number goes up, the number of deaths will go up. And then secondly, the number of people who can get treated. As the number of people who can get treated goes down, the number of deaths will go up. So there's an inverse relationship there. Okay, so those are really the two main things that I see as issues. And so you could create, potentially, an equation that relates the number of deaths, this would be what we call the objective function, the number of deaths as a function of the number of people infected and the number of people who can get treated. Okay? Now, there's a lot of constraints on those other two numbers. All right? The constraints are things like the number of hospital beds in a given area. Okay, that's a constraint. If you have a maximum number of hospital beds, then you have a maximum number of people who can get treated. If you have the number of ventilators that are available is another constraint. The number of healthcare professionals that are available to help and healthy is another constraint. And so there are all these different constraints. Another constraint on the number of people getting infected is how many people you come in contact with. Okay, so you try to limit that. And so these are all different types of constraints. And if you had some formulas, some equations to relate those things, you could establish a way to optimize, or in this case minimize, the number of deaths. Okay, and I think that's what the government and is really trying to do. The government and the CDC and whoever else is involved in this. Okay, we're trying to establish those things. So that's just an example. Now, in this section, I'm not going to go through. We're not going to do a lot of practical applications like that. I really just want you to get a feel for the actual calculation and the theory behind it. So basically what's going to happen then is that you're going to have some sort of constraints given, and they're going to be given as a system of inequalities. Okay, so it's going to be a whole bunch of inequalities here, and let's see, system of inequalities. And then you're going to have this objective function. The objective function is, the system of equalities is going to have two variables in x and y, right? Just like we saw in the previous section. So the objective function is also going to be defined with x and y values. So, but it is often a third variable or third item that we're trying to minimize or maximize. And so that third one we're going to call z. So the objective function is going to be, we're going to call it z, a third variable, and it's going to be some function of both x and y. Okay? This is what we're trying to either maximize or minimize depending upon the problem. And it's going to be, and we're trying to optimize it over these constraints, okay, or under the constraints, I suppose. The constraints give you some sort of region, some sort of graph, okay? So if you imagine these constraints giving you, maybe some sort of weird region like this, kind of like we saw last time with the system of linear inequalities, then the objective function is a separate function from this. Okay, the region is defined by the inequalities. The objective function is separate. But what you can imagine is picking points inside this region. They have xy coordinates, and you plug them into the objective function. And you do that for another point. You do that for another point, and another point, and maybe a point over here. And if you took every point in that region and plugged them into the objective function, the question then is, what point gives you either the lowest or the highest value, depending on the problem? Okay? Now, what you'll always find is that we're going to be dealing with linear objective functions. Okay? Ours are going to be linear. And what that means simply is that x and y are raised to the 1 power. Okay, they're not squared, they're not cubed. We're not dividing by an x. They're just very simple linear objective functions. And when that's the case, the minimum or maximum value will always occur on a corner. Okay, so we'll say the optimal value, again, optimal means maximum or min depending on the problem. The optimal value always occurs at a corner. I don't know what I'm writing there. Okay, always. So it's going to be, that corner, that corner, that corner, that corner, whatever the corners are of that region. So the main thing is, when we do these problems, is we have to first find the region, find the coordinates of every corner on the region, plug those coordinates into the objective function, and see which corner gives us the lowest or highest value depending upon what the problem is asking for. Okay, so we'll try an example here in the next video.